First step is standardization. Second is to compute the covariance matrix. Third is obtain the eigenvectors and eigenvalues from the covariance matrix. And fourth one is arrange the eigenvalues in descending order and choose the k eigenvectors. Here in the fourth step, we have to construct a feature matrix. Okay, so you saw the first three steps more in detail. Today we will see the feature vector. So in the step one, what is the step one? Why do we go for standardization? It's an important question. To bring all the column values to a common range, right? You have to bring all the column values to a common range to avoid getting the biased output, right? So what happens if you do not standardize the value? Computation time will be more and obviously the performance also goes down. Second one is computing covariance matrix. This has already been discussed. How do you compute covariance matrix? You saw this example. Next is next step is calculate the eigenvectors and eigenvalues from the covariance matrix. Here we are basically identifying the principal components, okay, or the feature vectors. Next is here, can you see the link? I have included the links in the slides. You can open the links, you can go through the links to study eigenvectors, eigenvalues and covariance matrix. And yes, you saw how the principal components are generated, and you also know that the principal components or the feature vectors containing the data points of high variance contain the most useful information, and they are represented through eigen vectors. So here there is one more link to study the eigenvectors and eigenvalues. And basically eigenvalues and eigenvectors play an important role in finding out the principal components from the data sets to reduce the dimensions for better visualization. So you saw this example here. You took a data set, two-dimensional data set with variables, and these are eigenvectors and these are eigenvalues. And you also learned how to compute the variance, right? So you, in the last class, you calculated the variance of lambda1 and lambda2. What is this V1? V1 is a eigenvector which corresponds to PCA1. V2 is the second eigenvector which corresponds to PC2. So now what is the next step? Next step is to sort these values, eigenvalues, in descending order. So obviously we can find that eigenvalue lambda1, variance of lambda1 is giving us 0.96318, that is 96%, and variance of lambda2 is giving us 4%, that is PC1. This PC1 carries 96% of the variance. PC2 carries only 4% of the variance. So till now you learned in the previous class. The next step is feature vector. What is feature vector? So here in the previous step, you learned computing the eigenvectors, and you also learned to sort the eigenvalues in the descending order. Okay. Now in this step, what we do is we select or we choose the components or the eigenvectors which are of high significance. That is, we have to decide which all components should be selected, which all feature vectors or which all eigenvectors should be chosen from the data set. So what we do, we keep all the components, which are of higher variance and discard the components which are showing lower variance. We are discarding or we are dropping the column values which are showing low variance, or those low variance are represented through low eigenvalues. So what exactly we are doing? We are selecting the columns which are high eigenvalues showing high variance and dropping the ones with lower eigenvalues, then forming a matrix called feature matrix or a feature vector. What is this? This is a matrix that contains the principal components. It is a matrix that contains the columns that having higher variance. So this is the first step towards reducing the dimension of the data set. Let us say if there are n columns in the data set, and if we choose only the first p values, p vectors out of n, the final data set will have only p. That is, we are selecting only p, and final data set will have only p number of dimensions through projections. So here, let us go back to the earlier example. Here we have vector 1 PC1 value, this value PC2 value, and these are eigenvalues. Now it is up to us whether to combine these two values, like here, to train the model, or choose the one which has higher variance. So we are PCA, PC1 has 96%, PC2 has 4%. So it is up to you whether you want to combine these two vectors to train the model, or select the highest one. This contains the highest variance, or select this one. So in this case, I have combined both. In the second case, I have taken only the first PC component. So, okay. So now this feature vector contains the resultant vector, either this or this, depending on the developer's wish. So here, in this case, in the second case, I'm dropping this second column. I'm dropping V2, right? This is of lesser significance, and forming the resultant vector, this is a feature vector. This becomes the feature vector. Discarding the eigenvector V2 or the PC1, what will do? It will reduce the dimension by 1. Here it is 2 dimension. Now here it is reducing the dimension by 1. And obviously it will have the loss of information. How much? Only 4% loss. If I discard this, I will have only 4% of loss in the information. And this 4% of loss of variance is not that important. I still have 96% of the variance through PC1, right? So it is up to you whether to choose both or select the one with the higher variance. So this resultant feature vector contains the matrix of the columns showing the higher variance. So next, the last step is, so not last step, there is one more step ahead. So here in this step, what we are doing, we are recasting the data along the principal component axes. So what exactly we are doing here? So in the previous step, steps 1 through 4, what we are doing? In standardization, we are processing the data set, right? In standardization, we are bringing all the values to a common range. Except standardization part, in the steps 2 to 4, we are not making any changes to the data set. We just select the principal components and form the feature vector. Okay, form the feature vector. And here, so far, the input data set always remains in the original feature space. Okay, we are not disturbing the data. Except the standardization, we are not touching the data set. We are not disturbing the data set. The original data set still remains in the original axis. That is, it is available in terms of initial variables. So in this step, what we are doing is, here the main aim is to use the feature vector and reorient the data from the original axis. Okay, here what, just a minute, I'll show you. So what we are doing here, we are reorienting the data from the original axis to the ones represented by principal components. So the name is principal component analysis. So here original data points are the blue points. We are reorienting the data through this vector. These data points are reoriented in red dots. So this is called recasting. We are reorienting the data points through the newly formed feature vector. And how it is done? There is an equation. There is an equation. How it is done? It is take the original data set, take the transpose of it. So here transpose of the original data set is multiplied with the transpose of feature vector. This is giving us the final data set. So how this recasting is done? Here recasting is done by multiplying the transpose of the original data set by the transpose of feature vector. So now this recasting is done using this equation. So next step is now we'll see how PCA is implemented in Python. So let us recap. First is standardizing the data. Standardization, here we have to standardize the value with mean 0 and variance 1, compute the covariance matrix. Next is obtain eigenvalues and eigenvectors from the covariance matrix. And next we have to order the eigenvalues in descending order. Yes. Next, construct the projection matrix W from the selected k eigenvectors. What exactly we are doing here? We are constructing a feature matrix. Okay. Then transforming the data set via projection matrix to obtain the principal components, that is represented through a feature space Y. So here, go back to the data set. This is a data set, iris data set I have pulled from GitHub, and this iris data set contains 140 observations and 4 columns. Okay, it has, sorry, not 140 observations. I think it has, yeah, it has 150 observations starting. These are the values. Yes, it is starting from 1. So there are 150 observations and 4 column values. 4 attributes: sepal length, sepal width, petal width. All these values are in centimeters. Okay, so taking this as a data set, we'll move on to the procedure, PCA algorithm. So what is being done here? Can anybody say, guess? What are we doing here in this step? Go through the code. The procedure remains the same, is as usual. Import pandas, import numpy, matplotlib for data visualization, scikit-learn for this PCA component. This is PCA built-in function is accessed from this sklearn, and for standardization you are importing from pre-processing. Next, matplotlib inline. These are all same. And now this iris data set, this is the source I access from here. So next, I'm taking the last 5 columns from the data set, because you cannot visualize all 150 observations, right? So read the either first 5 columns or last 5 columns. So these are the 4 column values, and classes is Virginica. Here in this data set there are 3 classes: iris setosa, iris versicolor, and iris virginica. So we have to do classification for these data sets. So here, what are we doing? This is the data. This is why we have to separate independent variables and dependent variables. That's what I'm doing here. I'm separating independent variable X, and here this is Y variable. Please look at this carefully. Iris setosa, this is a Y variable because we are using this towards the end. So separate the target variable from the column values in Y array and rest of the values in independent variable X. So that is done using this code. And this is the Y value. And I have already told that the data set is available in the form of 150 into 4 matrix, 150 observations and 4 column values. So here the columns are the different features here. Okay, the columns here, these are the different features, and every row represents a separate flower sample. Okay, till here, from here till here, 51. This is setosa. Similarly for versicolor and virginica. Okay, so now each sample row X can be pictured as 4-dimensional vector. Okay, next here, first one is, what is the first step? After this we are separated X and Y. First step towards PCA is standardization. So here use this built-in function X standard scalar, and you are bringing all the column values to a common range. So what exactly is being done here? Go through the code, just try to analyze what is being done here. You have to transform the data onto the unit scale, that is mean is equal to 0 and variance to 1, and this is essential to get the optimal performance of this PCA algorithm. So standard scalar, it's a method class. Here fit transform, this is a these are all, you will learn this by practice. Okay, see how the codes are used for standardization. And what you see here, what do you see here? Here this output, you will see all standard values, all values are standardized in terms of -1 to +1. Values are between -1 to +1. So this is how standardization is done. Second step is computing eigenvectors and eigenvalues, that is called eigen decomposition. So how it is done? Which built-in function is used? See, this is the beauty of Python language. Python has a rich set of built-in functions. Okay, it's not like your C, C++, Java. Python is a beautiful language. It is a very rich language. The more you do coding, the more functions you will explore. Okay, so how second step is to compute the covariance matrix. So you already know what is covariance matrix. Covariance matrix is basically used to find the highly correlated features, which all columns have high covariance, which all columns have low covariance and all. So to determine this, we compute the covariance matrix, and here we use NumPy array. Okay, here we use NumPy array NP, okay, and calculate the mean x's here, xt shape, and you go through this code, you are in final year. So this is the covariance matrix, presuming eigenvalues, eigenvectors and covariance matrix. So here you get the covariance matrix. Next step, eigenvalues, eigenvectors computation from the covariance. Here you've got the covariance matrix. Now you have to compute the eigenvalues and eigenvectors. So here again, linear algebra, how to calculate eigenvalues, eigenvectors. That will be very helpful if you know these concepts. Those who do not know, please revise these concepts. Links are already given in the slides. I will share the slides after this class. So here use NumPy array again to calculate the eigenvectors and eigenvalues. Okay, and what do you get here? You're getting eigenvectors and eigenvalues, and see how the functions are used. Look at these codes. What is this parameter? What does it indicate? X standard T. Anybody?
Transpose.
Sorry?
Transpose.
Okay. So now eigenvalues and eigenvectors are listed here. Next step is you have to verify the eigenvectors. So verify the eigenvectors. Here, please make a note that the sum of squares of each value in an eigenvector is 1. You can write down the sum of the square of each value in eigenvector is 1. Now let us see whether it holds. It means we have computed to check whether we have computed the eigenvalues correctly or not. So what we have to do, what we are doing here, take this first values, okay, 0.27 plus 0.1386 plus 0.5198 plus 0.06. So the sum of the squares of each values in eigenvector should be 1. So now take this, calculate the sum and find out if it is 1 or not. If it is 1, what does it mean? What does it mean? Yes. To check whether the eigenvectors computed correctly or not. Okay. Next step is, here you have got eigenvectors. Next, you have to select the principal components. You have got list of eigenvectors. Now you have to choose which all eigenvectors you have to select in order to reduce the dimensions. For that, you have to arrange the eigenvectors, eigenvalues in descending order. If there are m total number of eigenvectors, eigenvalues, you have to choose the top k features representing the k eigenvalues. Okay. So now you have sort the values. In this case, what I am doing, instead of taking all the eigenvectors, I am taking the eigenvectors that are showing high variance. Okay. So now here, go through this code. And here I am getting eigenvalues in descending order. Top 1, second, top, third, fourth. These are the eigenvalues listed in descending order. And next is explained variance. What does it say? What does it say? Explained variance indicates, it shows which all columns have high variance. Again, it is helping us to find out the principal components which carry the most useful information. Okay. Go through this code, how it is being done. Previous step. See, the eigenpairs, eigenvalues, there are built-in functions for covariance matrix and finding out eigenvalues and eigenvectors. So next step is explain variance. After sorting the eigenpairs or eigenvectors and eigenvalues, the next question is, how many principal components we are going to select for our new feature subspace. Okay, this can be learned through a component called explained variance. This explained variance is calculated from the eigenvalues. So what does it say? This explained variable indicates how much information or the variance can be attributed to each of the principal components. So this is how the explained variable is found out through the code. Go through the code line by line. And here you are getting the explained variables, cumulative explained variance explained. First one variance explained, second one is cumulative variance explained, third one is percentage of variance. The first two principal components each contain percentage of variance. The first two principal components together contain. So it is showing us the value variance of individual vector as well as the combined vectors. Next, the fourth step is to construct the projection matrix W from the K selected eigenvectors. So how it is done? So this projection matrix is used to transform the iris data set, that is 4-dimensional data set, onto new feature subspace. That is how the data is extracted and how it is projected onto a newly constructed eigenvector with reduced dimensions. We can say a newly transformed data set with reduced dimensions. So what is this matrix? It is a concatenated matrix. It is a matrix of concatenated top k eigenvectors. And here what we are doing, we have 4 columns. We are trying to reduce it to by 2. So instead of 4, we are reducing the dimension to 2 features subspace by choosing the top 2 values. We have 4 columns, but we are finding which all columns have high variance, and we are selecting only the top 2 values for the projection matrix. That is a W. That is matrix W. So newly transformed data set. This is how the newly transformed data set appears with the reduced dimensions. 4 columns are here. Again, it's reduced to 2 columns. And the last step is you have to project that matrix onto the new feature space. So how it is done? Again, here 150 into 4 is reduced onto 150 into 2. Just go through the code. In this step, this is the last step, right? Here we are using 4 by 2 dimensional matrix W to transform into a new feature space using the equation y is equal to x into W. So what is y here? Y is nothing but the output matrix. It will be in the form of 150 into 2. First column represents the principal component 1 and second column represents the principal component 2. So this is 150 by 2 matrix. It is a projection feature matrix. So here we can combine the principal component 1 and 2 and taking the earlier data set y value. This will be the final matrix. This will be our principal component matrix with the class. The output is output column value. So what exactly we are doing here? Just go through the code. What exactly we are trying to do here? Here we are combining the target class variable, okay, which we separated it in the very beginning step, right? We bifurcated x variable with the y variable. So we separated y variable. We are combining here along with PC1 and PC2. Okay. So now this is projected into this is a 2D data, dimensional data. Now we will visualize this 2D data into 2D projection. So next. PCA, how this PCA is projected into 2D. Instead of visualizing the entire data set, we are extracting only the 2 columns with high variance and we are projecting it. So taking this code, this is how the 3 classes are projected. And here these 3 vectors, there is a vector representing the red dots, another vector representing the green dots, third vector representing the blue dots. So here our red dots represent iris setosa, green dots represent iris versicolor, blue dots represent Iris virginica. All these three classes are categorized into different groups, and they are projected through principal component 1, 2, 3, and which are 90° with each other. So there are built-in libraries to directly compute the principal component analysis. So here there is a function, built-in function PDA. So PCA is equal to PCA, n number of components 2, and here you can give the percentage as a parameter to the PCA. If you give PCA 0.95, it means we want to include 95% of the variance, and the PCA will return the number of components which describe 95% of the variance. If you include PCA 0.75, it will show 75% of the variance, right? So here it takes PCA is equal to PCA 95, it is showing 95. PCA 7.75, it is showing 7.75. It is up to you to decide to set the level of performance. Okay. And since in the previous slide we are selecting only 2 components, here we are giving number of components as 2. You can choose all the components, no problem. But here it is my wish, I can take only 2 components. Number of components is equal to 2, and usually how the data set is displayed, it is displayed in top 5 rows. This is how the PCA1 and PCA2 are projected, and combine data with the Y variable. The first component contains, here the first principal component contains 72.77% of the variance. Second principal component contains 23.03% of the variance. Third and fourth principles we have not included here, okay, because assuming they are containing very less variance. So PCA use cases. PCA are usually used in image processing, movie recommendation system. They are used to optimize power allocation in various communication channels. In companies, actually, in financial institutions, we do not use PCA. We never go for PCA. Instead of PCA, we go for feature engineering techniques. So if the time permits, I will teach feature engineering towards the end. Please remind me towards the end. PCA is just to build your basics strong. Okay, so you are learning PCA in this semester to learn how the dimensionality reduction works. Any doubts so far? And PCA is included for the midterm 1. Am I audible? Hello?
Yes, ma'am, you're audible.
Ma'am.
Yeah, thank you. So till PCA, you will have midterm 1 portion. So you can pull any data set from the Kaggle, and regarding SVM, try to take the smaller data sets for SVM. If you take larger data set, it will show you magical results. Sometimes you get errors which you will never be able to detect. So SVM doesn't work well for larger data set. Okay, for SVM take smaller data sets. For PCA you take larger data sets. So what are you understanding from this diagram? Who will tell us clearly after studying all the steps from PCA? Let me see who will explain this. Otherwise, I'll pick randomly. response? So there are many number of data sets available under Kaggle, GitHub. Okay. So pull data sets, practice these two, come prepared for exam. Priyanka, are you there?
Yes, ma'am.
Yeah. If you want to discuss anything about the test, midterm test, you can. I'm done with PCA now. We still have time, so.
Yeah, I don't have anything to specify. Portions are till PCA, including PCA.
Yeah. Next class, I'll be starting clustering.
That topic is not there for your midterm.
Yes.
Ma'am, is midterm is objective or descriptive?
Mostly subjective, but you may have problems. Descriptive, very, very less questions, even if you have. Is that okay?
Yes, ma'am.
But problems you have to go through. You may have problems, but like writing theories of a large answer, etc., will not be there. Short answers, if at all you have, it might be maximum short answers like.
Okay, okay. I am uploading the PPT now. PCA.
I was audible, no? Like I think I got
Yes.
disconnected in between.
No, you were audible.
Okay.
Yes, PPT has been uploaded in the Teams. You just go through the PPT and notes.
A little more clarity on the type of questions, maybe by Thursday I'll confirm. Thursday evening or something. Okay. But as such, you won't have long answers to be written. Mostly problems and one word kind of answers.
Okay, ma'am.
Any doubts in PCA? If you have any doubts, please ask. I'll be very happy if you ask doubts. If you don't ask, it means either you don't understand anything or you have understood completely. Isn't it, Priyanka?
There can be other cases also, like they're not here. A few of them are there, of course. Others maybe just they're thinking we'll see when the
They
exam
are
comes.
just showing their presence virtually.
Today also I can see only 65. So what is it? A company is going on still? Students, what is the status? One of you unmute and say what is the situation. Today, is there a placement going on for you all? Yes or no?
Right now, we don't have any, ma'am. Like in the afternoon, like 4 o'clock, we have one company coming.
Oh, okay.
Which
What happened to Wipro? Like it's over? All the steps are over? Like interview is also over for Wipro?
No, ma'am. I think only the exam was over.
Okay, okay.
Even the results are not out.
Okay.
Will there be any further rounds for Wipro?
Yeah, yes, ma'am. Interviews will be there.
Today, which company?
Today,
Alstom, ma'am.
Which one?
Alstom.
Okay, Alstom. Okay. It's in Balandur, I think. Okay, shall we wind off, Priyanka?
Yes, ma'am. If they don't have any queries, we can find. No problem.
Okay, fine. Okay, students. Okay, Priyanka, bye. Bye, everyone.
Bye, everyone. Thank you.
Ma'am, can you stop the recording?
Sure, sure, sure.
Thank you.